In this video, we'll cover two topics, the third law of thermodynamics and also standard entropy. So let's go into the third law of thermodynamics. I want you to take a look at this image over here before I could describe third law. Now here on the left, it says 0 Kelvin, and it's kind of a little hard to see, so let me zoom in. So that's 0 Kelvin, and then we have on the right, increasing temperature where the Kelvin is now positive and it's going up and up. At 0 Kelvin, this is when entropy is 0. This is what we consider to be the absolute zero. There is no movements, and the molecule exists as is. There's no vibration going on. There's nothing. So based on the third law of thermodynamics, the entropy of a pure and perfectly crystalline substance at 0K is 0. It's saying the entropy is 0 at 0K. Now, so in other words, at that absolute zero, there's no movement, meaning that there is no matter dispersal. Matter is not dispersing. There's no energy dispersal as well. So that means there is only microstate of 1. And if you recall, the entropy original equation is this right here. And you can see that entropy is equal to the constant, Boltzmann constant, ln of W. Well, if the number of the microstate here is just 1, ln of 1 is actually 0, so the entropy becomes 0. So microstate having only one microstate, which is rarely the case, is going to be make the entropy 0. Taking that 0 Kelvin as its reference. So we need to scale it somewhere. That's where 0 as a reference. And now let's take it up to a temperature and a condition where it's 298.5 Kelvin, or also known as 25 degrees Celsius, and a pressure of 1. Now you're at a point what we consider to be the standard entropies. The other place was at an absolute 0. Now we're after the third law of thermodynamics says, now we're taking that as a reference, and then we increase the temperature at 298. Well, scientists had measured all these entropy of the molecules. So here are a list, just few of the list of a really long list of the molecules. So you see a substance like C carbon graphite that has the entropy of 5.740. Notice the units, there's joules on top and you have a Kelvin on the bottom. Now I haven't mentioned moles yet, but now I am going to use them mention the moles, but there's also moles on the bottom. So if I were to rewrite this in a more of a simplistic format, entropy unit will have a joules over mole Kelvin. You might see in textbooks and other resources joules mole to the first power, negative first power, and then K negative first power. And they're all equal in units. So nevertheless, all of these guys are at standard state. At 1 atm and at 25 degrees, what is the entropy? And notice that none of these are 0 because they're not at the absolute 0 state. Okay. This list is a shortened version. There's a really long version in your reference sheet, so make sure you check that long version. There's a column of entropy and enthalpy and Gibbs free energy, but we want to focus right now on that S, and I will utilize this particular table for the videos. We know delta S based on the table here, but what about the change in delta S? Say a molecule, for example, if you have a carbon dioxide and we're going to add it with some other substance to form a completely different compound, then what is the change in entropy that these goes through? Well, the change in entropy is represented by this delta S naught, okay? And you can compute that as follows. You say you have a reaction where A and B form C and D. Well, you take the entropy of the C and entropy of the D with its corresponding coefficient in the front multiplied. You add them together and then you subtract it to the summation or it added together of the reactants, which is A and B. And you find entropy of those and then add those together, incorporating also the moles that is in front of the balanced equation. In other words, we can take the summation of the product, entropy, minus the summation of the reactant, and then find the change in entropy, and we'll do an example now. Here it says calculate the standard entropy change, so it's asking for delta S to the naught for the following reaction. You have hydrogen and C2H4 forming into C2H6. So we're going to find those values here. So let's find the product first. Okay, so my product is C2H6. So my product is C2H6 is 229.5. So we set up delta S is equal to the summation of the product, which is just really entropy of the C2H6. We only have one. And the moles are here, and that's just there's just one there, imaginary one, so we don't need to write anything. So I'm just going to put one there. And then minus the summation of the reactants. And what are the two reactants? We have a hydrogen and C2H4. So for hydrogen gas right here, that's 103.57. So we write this is for hydrogen, and that's just 1 plus C2H4 Okay, now we're going to go ahead and plug in some values here. So for this one, 229.5, that's right here. And for hydrogen is 130.57. And then the C2H4 is up here to 19.5. So we want to do everything in the parentheses first. So 130.57 plus the 219.5. So now you have 229.5, and you're going to subtract that value. Second answer. And I would get negative 120.6. Negative 120. I believe I said 6, right? 6 joules per Kelvin mole. Let me double check that. Okay, so there we go. So negative 120.6 joules per Kelvin per mole, and it is negative, so this is a spontaneous process too. Let me we'll add that in, that this is a spontaneous process. Let's do another learning check. Here it says calculate the standard entropy change for the following reaction. So I want you to go back and see if you could find all of these molecules, the product and the reactant, in your in the reference sheet, and see if you could plug in some values here. Come back and check this video for the key. Hopefully you're able to get this, in that you were able to put the coefficient in the front of the entropy, and you found the entropy of the water, which is 69.91. So let me go back real quick. So I find water, H2O, and H2O, there's two forms. There's one gas and one is liquid, and the liquid is 69.91. So hence why I put 69.91 since it's liquid. So you have a lot of angles to sort of look at it. And there is a 4 there, so you need to multiply that by 4. And adding all this up, and you see this combustion reaction here, that was a negative reaction, which means that this was a spontaneous process.